Hello class, I want to work on this problem where you have a charged rod pitted against a charged arc. Now when you read a problem like this, it always helps to put it into a figure. So the semi-infinite rod has got a certain charge density and it's located along the x-axis. That's actually the negative x-axis here. Let's call that the origin and the positive x-axis. Now there is a semicircular arc that is of radius d. The radius d in the first and the fourth quadrant. So I'm going to indicate that arc like this. The traditional coordinate system would be the first quadrant and the fourth quadrant. And the rod itself starts at x equals d, negative d. So it's the same distance as that, so I'll place it there, and goes off to infinity. So this part, it just trails off to infinity like that. What we have basically got to do is find the electric field due to the rod at the origin, find the electric field due to the arc at the origin, and set them equal. That's how the electric field at the origin will be 0. Now I'm assuming that beta is positive. If beta is positive, then it'll send field out like this. If Q0 is positive, then it'll send field out like this, and they can cancel. However, if beta is negative, it'll suck the field in, and then Q0 also has to be negative. In any case, it doesn't matter because beta will turn out to be related to Q0, so whatever happens to Q0 will also happen to beta. Let's proceed to set up this problem and solve it. I'll first do the rod part. The charge element on the rod, dq, is located some distance x from the origin. And this is x equals negative d, and that is infinity. So the only caveat here is that the distance negative d, we may have to think about that a little bit. We'll talk about that soon. Let's go with finding out the electric field of the rod, which I'll call dE rod. Well, that's going to, I'll just indicate that. I'll assume that it's going to be positive and indicate that here. So that's dE rod. By Coulomb's law, that's K dq, and here again I'll indicate dq rod. Divided by the distance squared. That's what Coulomb's law says. So once you have this, we have to now find expression for dq. Well, lambda is just dq by dx. So that's given to us. It's beta x to the minus 2. So that tells me that dq is just beta x to the minus 2 dx. dq rod, that is. Put this back here, and I get dE rod equals k beta x to the minus 2 divided by x squared dx. And that gives me k beta x to the minus 4 dx. The electric field of the rod itself is got by integrating it from where the rod begins and where the rod ends. K and beta are constants, so I'll pull them outside, and I get minus d to minus infinity x to the minus 4 dx. If you use calculus, you'll use the formula x to the n, so x to the n plus 1 over n plus 1. So that's going to be x to the minus 4 plus 1, which is minus 3 over minus 3. Here's where we have to be careful about the interpretation of the value d. For infinity, so let me just go ahead and literally try to substitute and see what happens. If nothing happens, then I won't say anything. So it's k beta over -3. The upper limit is going to be 1 over infinity, negative infinity cubed, which is 0. You can be more careful here and write it as limit and so on. I won't bother. And the lower limit is going to be negative of this thing. So that's going to be 1 over d cubed. Okay, so my earlier comment does not really matter because I realized quickly that d is bigger than 0, so I don't have to worry about it. So this is going to be k beta over 3 d cubed. So that's the electric field at the origin due to the rod. And like I earlier said, if beta is positive, then that field points to the right. If beta is negative, it points to the left. Let's go ahead and now calculate the electric field due to the arc. Now this proceeds just like we did arc problems in the class and the notes. So what you do is it's traditionally defined. So I think it's better to take the angles to be from the x-axis. Call that angle theta. There's going to be an arc element on the charged arc, and we'll also take a corresponding mirror symmetry element on the other side at the same angle theta. So this will be called dq, and that will be called dq prime. These mirror symmetry contributions will cancel out one of the components. Let's find out which component will get cancelled out. dq will put out an electric field, again assuming the arc is positive, it'll put out an electric field like this. I'll call that dE. Since I've already written dE rod, I guess I should write dE arc, but you can also write it just as dE. dq prime is going to put an electric field along the same line joining it and the origin, and that will be called dE prime arc. It's very clear that the y components cancel out and the x components will add. This angle is also theta. So for the arc, from the arc perspective, dE net, the net arc charge, is 2 times dE arc cosine theta. Now we'll find out what dE arc is. For that, we need what dq is. Well, dq comes from consideration of linear charge density. So the linear charge density of the arc, I'm going to call lambda naught. So lambda naught is going to be equal to the rate of change of the charge with respect to the arc length, ds. Now this distance is d. I apologize for so many d's in the picture, but that distance is the same d there that you have in the problem. So by arc geometry, I have ds equals the distance d, and this is where it's going to get really bad, times the angle, which is d theta. So in retrospect, I should have called that capital D or something, just to make this a little nicer. But it's too late. Let's go with this. So I'll get dq equals lambda naught ds, and that's lambda naught, I'll write lambda naught and d together, times d theta. So it doesn't look that bad. Now we're ready to put, well, also separately, what is lambda naught? Lambda naught is the total charge of the arc divided by the total length of the arc. The circumference of a circle is 2 pi times the radius, so the semicircle has got length pi times the radius. So let me put that in there and get rid of that offending d altogether. So that's q naught over pi d times d goes away. Nice. So I just get q naught over pi d theta. So this has an interesting interpretation. The charge density, the amount of charge for any portion of the arc is just equal to the charge per unit angle times the angle. So that can be thought of as the angular charge density. Angular charge density times the angle equals the charge you have. Moving on, let's figure out what dE net for the arc is. It's 2 times dE, which is k dq, over r squared. R is, in this case, d squared, times cosine theta. So let me substitute for dq. So I get 2 k q naught over pi d squared cosine theta d theta. And now we integrate to find the total charge on the arc, the electric field on the arc, excuse me. 2k q naught pi d squared are all constants, so I can just pull them out of the integral sign. And I just have the integral of cosine theta d theta. What should be the limits? Be very careful here. We have used the mirror symmetry argument. Since the mirror symmetry argument has been used, we have already used the lower part. That's how we got the 2 factor. So don't double count. The integral limit is only going to be from theta equals 0 to pi by 2. Let's complete this. The integral of cosine theta is, well, what is it? It's sine theta, because if you differentiate sine theta, you get cosine theta. That's one way to remember your integrals. So 0 to pi by 2. And this gives me, the pi by 2 contributes, and you get a value 1, 0 doesn't contribute. So this just gives me 2k q naught over pi d squared. Now, that even though this comes out positive, we secretly know it is negative by the very way the diagram was drawn. So the electric field of the net electric field is actually going to point like this. And we have to have, it doesn't look like that, but we have to have these two equal. So that's the last step. Let's make them equal, and we've finished the problem. Require E rod is equal to E arc. So I get k beta over 3 d cubed is equal to 2k q naught over pi d squared. The Coulomb constant k cancels out. 2 factors of d cancels out, and so we have our beta here. Beta is just 2 q naught, actually 2 times 3 is 6 q naught over pi. So what happens here is the d goes above. This is making me a little nervous. It looks like beta has got units of Coulomb meters. So whenever you feel a little jittery about what you've done, it always pays to go back and look at the units. Lambda has got units of coulombs per meter. So if lambda is coulombs per meter, what are the units of beta? Well, the units of 1 over x squared are 1 over meter squared. So when I cancel out the meters here, the units of beta are indeed Coulomb times meters, which is the case here. So this is an excellent check to see if you've at least done all your algebra right, because if this came out to be anything else, you know that you made a mistake.